भार्गव सर आप अनम्यूट कर लीजिए माइक।
आवाज आ रही है मेरी?
Turn your microphone off. Banerjee, your microphone is off, so we don't hear you.
Yeah, I know that.
Okay, yeah.
Microphone talk.
Can you hear me now?
अरे बोलिए ना बाप.
Yes, sir, we can hear you.
Good day to all of you. The first speaker is Professor Qingming Cheng. He shall be speaking on the data-driven earth science learning and discovery. He has been president of IUGS and currently is professor at the School of Earth Sciences and Engineering, Sun Yat-sen University, Beijing. He has made seminal contributions to the development of application of modern mathematical geocomplexity theory for modeling nonlinear geoprocesses and for quantitative prediction of mineral resources. He is decorated with several prestigious awards. Professor Qingming Cheng, please.
Thank you very much. So good afternoon, everybody, or afternoon, depending on where you are in China's afternoon. I really would like to thank Professor Banerjee for this invitation, and also like to thank the whole organizing committee of the 36th IGC virtual meeting for taking the effort to arrange for this virtual meeting. It has been 2 years since the outbreak of COVID-19, which has affected our lives so much. And it also caused problems for hosting the normal session of the 36th IGC. I thank all Indian colleagues for your effort to handle the postponement of the 36th IGC. And I'm honored to be invited to give this plenary lecture on the data-driven earth science learning and discovery. Next slide, please. And I'd like to acknowledge the following organizations and programs for their support, that including IUGS EC, the International Association for Mathematical Geosciences, DDE, Deep Time Digital Earth, IUGS Big Science Program, Natural Science Foundation of China, and my universities. Next slide, please. During this talk, rather than the details of technical aspect of digital learning and knowledge discovery, I would like to first introduce an initiative of IUGS in facilitating data-driven earth science discovery, and to be followed by giving several examples to demonstrate applications for deep time digital data and a method for solving critical scientific problems in the field of Earth's evolution and extreme geologic events. Next slide, please. So I would like to bring you back to several years ago, 2026, when I was elected as president of IUGS for 2016 to 2020, and the promises and the proposed priorities for IUGS in front of frontier Earth science, especially along the lines of big data and the data-driven Earth science innovation. The critical questions at that time, including critical problems related to basic Earth science issues, as well as applied issues to support sustainable development of goals. Next slide, please. And one of the main questions and the challenges was how geoscientists and the geo community can make contributions to support the UN 2030 SDGs. And many of us know many of, if not all, activities and research, including research, energy, water, environment, etc., conducted by Earth scientists are directly or indirectly related to SDGs. Next slide, please. Based on reviewing some of the documents and the strategic plans of various international organizations, as shown on the right column of the screen, that including the International Science Council, UNESCO, GeoUnis, and many other organizations. I listed the keywords frequently appearing on this document, which is listed on the left column of the slide, to show the what are the current frontiers of the Earth sciences. The keywords ranked at top include data science, data analysis, computation, transdisciplinary uncertainties, etc. And the key challenges listed at the middle column include the understanding the geocomplexity of the Earth's systems, modeling the nonlinear geological processes of various kinds, and predicting extreme geological events with uncertainty. These ideas and information are included in my president report published in IUGS e-bulletins. Next slide, please. One of the strengths of our Earth science is the rich data we generated by various means, including field survey, mapping, analytical analysis, as well as simulation detections. This gives us multi-scale, multidisciplinary, and multidimensional Earth big data. The question is how to effectively use this data, and that poses a challenge for geoscientists. Next slide, please. Meanwhile, with the big data and data science technology, including artificial intelligence, geoscientists can investigate the fundamental issues such as co-evolution of Earth's environment, Earth's life, and Earth's materials. So additionally, these type of issues are studied separately and also often quantitatively. Next slide, please. Of course, the applied questions also include questions, for example, convergent plate boundary dynamics and their effect on natural resources, the environment, hazard, and even human resilience. The questions can be big data discoveries for resource assessment, for example, on Africa continent, or the predictability of extreme geologic events such as earthquakes, volcanoes, and the landslides. And this type of issues are global issues related to many nations and need broad collaborations. So from yesterday's talks given by various speakers also indicated that this kind of geological science in nature, that is, we need a more collaborations. Next slide, please. The digital revolution now being recognized as challenge domains by the International Science Council, which remains as the current frontier for science. The big data and technologies of data revolution combined with the transdisciplinary and integrative effort can boost innovation and discovery in fundamental as well as applied earth science research. Next slide, please. So for several years, we trying to, as IOGS EC, trying to find a way to promote our science along the lines, particularly in a digital technology evolution. And so at the, for about two years, we did quite a bit communication, promotion, preparation, and consultation with the international organizations, including International Science Council, UNESCO, and the GeoUnis, AGU, EGU, GSA leaders, as well as many constituting groups of IOGS. And finally, we have this idea of to do a big science program. So at the 72nd IOGS EC meeting held in Potsdam in 2018, the proposal I proposed to establish IOGS Big Science Program was accepted, and we set several criteria for project selection. The view was that the digital technology can help to scientists to make transformations in at least three aspects. First, from question-driven to data-driven research. Second, from human learning, human reading, and human intelligence to machine learning, machine reading, and machine intelligence. From no questions seeking unknown answers to discovery unknown questions and seeking unknown answers. Next slide, please. So, as I said, after quite broad consultations, a year later, we had this idea of deep time digital Earth. Actually, initially in 2018, I had this proposal we called a deep understanding of deep Earth, also called DDE. I proposed at the General Assembly of International Science Council in Paris, 2018. But later we, revised with the comments from IOGS bureaus and EC members, as well as other colleagues, changed the title of the proposal to Deep Time Digital Earth. And so that proposal was accepted by the IOGS EC, and also EC proved to have a IOGS EC meeting in conjunction with a DD forum to be held in Beijing in February of 2019. So at that forum, we formally announced the Big Science program and kicked off it. So it attracted about 250 scientists from all around the world, representing not only like ISC, UNESCO, the GeoUnis, but also more than 40 IOGS constituent groups that including adhering committees, affiliated organizations. The programs and activities attracted quite great deal of attention in the media. For example, Science Journal published the news on the same day saying Earth scientists plan a geological Google. Next slide, please. The primary goal of the DD program was to develop a open platforms of connected geoscience information efforts with fair data. Fair data means data can be findable, accessible, interpretable, and reusable, linking various Earth spheres, hydrospheres, geospheres, atom spheres, and the biosphere in geoscience geological history. Thus, the data in more than 3 dimensions can be utilized for supporting transformative studies of evolution of Earth, including its life, environment, and materials. Next slide, please. So in the remaining talk, I will use several examples to show how data science technologies can be used for facilitating Earth science discoveries. Next slide, please. So I choose examples of using big data plus mathematical models plus supercomputing for study unknown but complex questions related to geological extreme events. The events could include evolution of Earth's life or biodiversity, materials such as minerals, and the environment, including tectonic related magmatic and sedimentary events. So one of the challenges of using deep time data to study major geological events is its incompleteness and the variable quantity of the time series data. Due to the limitation of the sampling and the sample representatives, as well as the recycling geological process, which make it impossible to have samples to cover the complete domain of the studies, either spatially and temporally. So the older the media such as rocks and sediment to collect the sample, the weak the values of the samples. Therefore, a typical problem is the weak anomaly or weak signal and incomplete time series data to be used for analysis. Therefore, specialized techniques and the mathematical models need to be developed to overcome this kind of problems. Next slide, please. So this slide lists a few examples to show predicting resources in frontier regions, including deep earth covered regions, such as regions covered by transported materials, deep ocean, and deep space. The graphs on the slide show, let's say, from pre-processing remote sensing images and fusing images for detecting alteration zones for mineral potential, to the right, more complex processes for resource assessment and prediction. For example, predicting deeply buried mineral resources in a covered area, as shown on the upper right graph, and energy resources, including oil and gas under the ice in the Arctic region, as shown on the left lower graph, real earth elements, resources in sea mud in oceans, and the liquid water on Mars by radar technology, as shown on the lower right graph. So this type of studies are not a traditional type of geological works because they involve data and data models and computing for predictive purposes. Next slide, please. So this is another example of research conducted by Dr. Bob Hansen and his team in Carnegie Institute for Science. The researchers used machine reading, knowledge graph techniques, plus large number of mathematical models to extract information of minerals and age of formation from various databases, including EarthCamp, PaleoBio database, so that they can create frequency distributions of minerals against the age of the Earth's evolution. So this distribution allows us to make accumulation curves and to create a large number of rare event theoretical model to predict the total number of mineral species. Therefore, we can estimate what are the missing mineral species. For example, it was predicted at that time in the paper about 145 missing carbon minerals and about 1,500 missing minerals of general species, which remains to be discovered. And the paper also led to the discovery of 15 new carbon mineral species, which is remarkable. But the most remarkable part of the work is that it has taken mineralogy from being an entirely descriptive science and transformed it into a predictive science. Next slide, please. So this is an example of research conducted by Professor Fanjun Xian and the Chinese Commission Su Junsen at the Nanjing University in collaboration with others, including myself, on creating a high-resolution biodiversity curve. As we know, reproducing the changes in biodiversity through incomplete fossil data is a major scientific problem. And these researchers used paleontological big data, supercomputers, and genetic algorithms to reproduce and identify periodicity of the biodiversity evolution based on fossil data. So this example, as shown on the screen, is about a Paleozoic marine biodiversity curve from about Cambrian to early Jurassic, covering about 300 million years of time, was reconstructed with a temporal resolution of about 26,000 years, which is 400 times more accurate than the similar existing international studies. So based on this high resolution curve, modern time series analysis can be further utilized to identify potential cyclicity of the events. So this work was published in Science in 2020. Next slide, please. So this is another research conducted by my group in collaboration with colleagues from Queen's University of Canada and the University of Wisconsin, America. The study is based on the database from the microstrata, a data platform created by Professor Shana Peters' team in University of Wisconsin. So this platform uses supercomputers and machine reading techniques to extract geological data relevant to spatial and temporal distribution of sedimentary, igneous, and metamorphic rocks, as well as data extracted from them. For example, on April 14, 2019, so that day when I compiled this slide, from the microstrata website, it indicated that day the system read more than 5,000 papers at about 240 per hour. So for this particular research, let's say it is based on the marine sediment flux data as shown in the left graph. You can see that the graph shows that the values of frequencies of, or the values of sediment flux for old age is very weak, very low in comparison with the flux in a relatively new age. So this is a very typical problem of deep time data. And a new method has to be developed. So we developed a new method termed local singularity analysis based on the concept of fractal density developed by our group. This method was used to process data series data, which reveals remarkable cyclicity of the sedimentary record as shown in the middle graph, and also the cyclicity of the sedimentary record and associations with the separations aggregation of the supercontinents. So you can see it in the middle graph that the lower anomalies are spatially, temporally correlated with the aggregation of supercontinents. So this discovery supports the hypothesis of the sediment can act as lubrication to promote plate subductions, which result in a loss of sediment flux. So this work was just published in EPSL 2 months ago. Next slide, please. So the last example I wanted to introduce is a research I did on analyzing global detritus, zircon, uranium, and lead age data and other type of data to study epithetical and periodical evolution of the Earth's continent. So this paper was published in Governor Research. I should thank Dr. Santos for reviewing the paper and they gave a good comments. So from this, the data, the global data, we can see that the peaks of the frequency distributions are generally corresponded to the no supercontinent. The question is that, are the magnitude of the peaks meaningful, and can we extract any information about the evolution of the continent from the data? Next slide, please. So I analyzed about a 250,000 data from the literature, and I used the local singularity analysis method as a scaling high-pass filtering technique to the data. And so you can see the graph on the right lower graph, and that reviewed a quite nice trend. That is episodic increase of the frequency, but a decrease of the magnitude of major magmatic activities peaks. So by extrapolating this singular trend of the peaks and also integrated with the mantle temperature trend, so we concluded that in about 1.45 billion years from now, the singularity or the intensity of magmatic activities were diminished, and the temperature of the mantle temperature were reduced to below 1,100 degrees, that is below the solidation, rock solidation temperature. Therefore, 1.45 billion years could be the minimum future age of the plate tectonics. Okay, so this, as I said, this result is published in Government Research. Next slide, please. So finally, as remarks of this talk, I would like to re-emphasize on the usefulness and opportunities of digital data science, technology for geosciences. I should say that the big data and the data science technologies with big data, mathematical model, and computing can change our way of research and also can empower our original innovations. Particularly the big data and artificial intelligence type of technologies can facilitate transformation of research from question-driven to data-driven research, from human intelligence to collaboration of human and artificial intelligence. Finally, from we know what we don't know question to we don't know what we don't know questions. Thank you very much. Thank you for your attention. Thank you.
Thank you, Dr. Cheng, for this interesting talk. Those who want to ask questions, they submit it in writing, and they will get their replies in due course of time. We pass on to the next paper by Professor M. Santosh and Dr. Cheng Shu Zhang. It's a very interesting topic, Radiant Earth to Habitable Planet. Professor Santosh is a very well-known figure in the geology. He was the founder, editor of Gondwana Research, and his contribution mainly pertain to petrology, fluid inclusions, geochemistry, geochronology, and to the very fascinating subject, supercontinental tectonics. He is recipient of many prestigious awards. Dr. Yang is a faculty at the China University. She has contributed to the material science, metallurgy, and crustal evolution of early Earth. Professor Santosh at present is professor at China University of Geoscience, Beijing, and also at Adelaide University, Australia. Professor Santosh, please.
Thank you, Professor Bhargava, and thank you, Professor Banerjee, for giving me this opportunity to give a talk at the 36th IGC, which is being organized in my home country in India. I would have missed it if actually many of us registered to participate in IGC, the actual IGC, which didn't take place because of the COVID. So it's my great pleasure and honor to be here today. and to also listen to my good colleague, Professor Chiming Chen's talk today on big data. And with me is Dr. Cheng Xue Yang, my associate and young colleague. This basically follows the the norms of IUGS and the IGC of participation and gender balance. So I invited actually Dr. Yang to join me for a gender balance of my talk. And thank you very much, Cheng Xue, for joining today. So we'll share the talk. She will talk about on a few slides. From Professor Chen's talk on data, with large data, how to process large data, and how to trace Earth history, various aspects of Earth history, including geosphere, biosphere, atmosphere, hydrosphere. I'm taking to a realm of Earth where we have no data. So we're going to deal with the topic with the zero data, which means many of the aspects which we are talking are recent models and ideas based on speculative models, basically. In fact, geoscience itself is what we call as an abstract science, because we are looking at the past most of the time. We really do not know what happened really. What we are looking at is the preserved history, the history which has been destroyed, a large amount of history which has been destroyed. We have actually no idea about that. So bear with me when I present some of the recent exciting models which are mostly speculative in nature. Next slide, please. As we all know, the birth pang of Earth took about 30 million years, means to create from a very nebula stage of condensed gaseous matter to the formation of magma ocean, through the fractionation, differentiation, formation of the core, and finally the big giant impact event, formation of the moon, to the birth of the Earth took almost 30 million years. And we believe that the Earth was, the actual Earth, that the primordial Earth was born at around 4.53 billion years ago. Next slide, please. This slide actually traces the summary of the history of the Earth through 4 billion years from its birth to recent. A number of events occurred during this long history, including, what we call as a solar luminosity increase, atmospheric oxygen content increase, and the oceans, the toxic oceans were cleaned up when plate tectonics was initiated into blue oceans. All this happened over 4 billion years. In fact, the first 4 billion years of history of Earth was the most boring period in the history of Earth. Although we call Earth as a living planet, as a dynamic planet, Earth was never a living or dynamic planet in its early history. As we all know, the modern life started only very recently, hardly 500 million years ago, what we call as the modern life forms. Next slide, please. I will hand over now to Cheng Xue to introduce you to how the Hadean Earth looked like. Cheng Xue, please.
Okay, thank you, Professor. So the word Hadean means hellish. It describes the initial state of our planet when it just started formed around 4.6 billion years ago. So after the initial formation, the planet was heavily bombarded by the asteroids, among which the most important are the Hydrous meteorites, which brought water to the Earth. Next slide, please. Thank you. Earth is termed as a living planet, and the most important component supporting life on Earth is the water and the atmosphere. You see, Moon is dry, and Mars has dried up long back. Earth has the most ideal conditions of a thin layer of ocean water that exposes the continent for weathering and supplying of nutrients. In case of super Earth in the universe, although it may have some ocean may be present, that could either be toxic or too thick that will not expose the continent to allow weathering and supply of nutrients. Next slide, please. The Hadean geologic history of the Earth is covered in mystery because of this, and no Hadean rocks are preserved on our planet. So the oldest dated mineral in the Earth is zircon. Next slide, please. This is the oldest, one of the oldest zircon. So oldest dated zircon is a detrital grain within metamorphosed sandstone conglomerate in Jack Hill from Western Australia. It is dated 4.4 GA. Although the most consistent age from zircon grades from this rock is dated 4.35 GA, around 200 million years after hypothesized time of the Earth's formation. Next slide, please. So since no hidden rocks are preserved on Earth, so we take Earth-Moon system for comparison, as the moon preserved the original signature since there's no plate tectonics on moon. As we know that the moon is mostly covered by an anorthosite crust with minor basalt. By analogy, it is speculated that the early Earth was also covered by an anorthosite crust. Next slide, please. So it is believed that initially the Earth was covered by a thick and hot magma ocean during its birth at around 4.55 GA. And where above the magma ocean, it has a thin comatiated skin. Next slide. So when the magma ocean starts solidifying, a top layer of basalt and comatiate formed, which was underlain by a thick layer of anorthosite. The anorthosite was also underlain by a creep basalt. So below the basalt, it is the thick cumulate with olivine and garnet. Comparing the Earth and Moon system, the Earth's anorthosite crust was around 35 kilometers in thickness, whereas that in the Moon was much thicker. It is around 300 kilometers in thickness. Next slide, please. So thus, the early Earth's history involved in two main stages. Look at the left figure. The first stage is immediately after consolidation of the magma ocean at around 4.53 GA. And look at the right side figure. It is second stage after the formation of the primordial crust and the initiation of magma convection. Next slide, please. So finally, here is a speculative model on how the hidden Earth's surface would have looked like after the heavy bombardment event. The anorthosite crust was dotted by comatiated volcanoes. There was possible presence of isolated lakes with a nutrient supply. That might have served as cradle for primordial life. So I come to Professor. Next slide, please.
Thank you. I'll take over from Chengxi from here. As Chengxi was just explaining to you that the very early history of the Earth witnessed a magma ocean and a big bombardment, or what the scientists call as the late heavy bombardment event, when probably meteorites as large as 1,000 kilometers reached the Earth. It's believed that Earth's water might have been transferred by these hydrous meteorites, which were delivered from the asteroid belt. There's one more recent concept which says that these meteorites might have also carried what's called bioelements. In order to, that in the later part of my talk, I'll discuss about the importance of elements, minerals, and rocks in the formation of life and sustenance of life. So one of the proposals is that these elements were initially transferred by these meteorites into the Earth from the space, actually. Next slide, please. This is one of the highly speculative but very popular models called the nuclear Geyser model, which is the possible speculated as the first birthplace of very early life. As you know, as Chengxi just told you, there could have been some isolated lakes in the primordial crust, which was distended, fractured, and water entered through the cracks down below. And at that time, we had enough of supply of radioactive heat by uranium and crete basalts, serpentinite and another mineral. So these boiling waters or geysers might have supplied nutrients for the early synthesis of amino acids. This is one of the speculative models called the nuclear geyser model. Next slide, please. Now, this is the most interesting part of the Hadean Earth. You know that one of the major challenges and questions in Earth history is that when did plate tectonics begin? When, how, and where did plate tectonics begin? There's a lot of debate going on there. Some people believe it began in the Archean times, maybe in the Meso-Archean or Neo-Archean. Some people even say, no, the real modern style of plate tectonics started in the Neoproterozoic. So this theory says that plate tectonics, the crude form of plate, what is plate tectonics after all? Horizontal motion of plates and subduction. This is what is plate tectonics, which is operating only on our planet in the whole solar system, or as far as we know. So when there was heavy bombardment by meteorites on an anorthosite crust, this crust was broken up or distended. And this heavy bombardment will also generate intense heat, temperature, and pressure. So what happens is this anorthosite will be transformed into eclogitic rocks, or what are basalts and anorthosites. So these rocks will undergo high temperature and high pressure, so-called, you can say, metamorphism. So they become highly dense. So the distended portions and dense portions will slowly start sinking down on both sides. So this crude, what we call as the ridge push and the slab pull force, if it had operated in the Hadean, this would mark the initiation of initial plate tectonics. We do not know whether it really operated because, next slide, please. Next slide, please. The plate tectonics, the most important component of plate tectonics, or the driver of plate tectonics, is water, oceans, because that's the lubricant for plates to move. We know from the example of Mars that Mars, there is no more plate tectonics because all the water had dried up, all water has been subducted into the mantle. So the plates have come to a standstill. So plate tectonics initiation is actually linked to the birth of oceans. And in turn, the initiation of plate tectonics is also linked to the birth of continental crust. And birth of continental crust in turn is linked to the birth of life, because continental crust is the milk for life, the nutrients. Next slide, please. So this is our problem. If there was an anorthostic crust at 4.6 or 4 billion years in the early Earth, like what we see on the moon now, we don't have any anorthosite of Hadean age left over on the Earth. So all the crust, anorthosite crust or primordial crust, have all been destroyed by, of course, by subduction. All this crust has gone deep down into the mantle. So subduction must have prevailed very early in the Earth history. This is the speculative model on what we call lost continents. The primordial continents were all lost from the Earth. Next slide, please. There is a fundamental difference between the modern Earth and the Archean Earth. I'm coming from Hadean to more to a period which we understand a little bit better than the Hadean. We know that the modern Earth is composed of large lithospheric plates, around 12 large plates, whereas in the Archean Earth, there were a large number of plates. It's estimated around 300 plates or microplates, you can call, and all these plates were moving here and there. That means we had a more number of subduction zones and more number of collision zones. The fundamental difference is that, as Professor Chen Qiuming was also mentioning, that the Earth is cooling down slowly, secular cooling, and he even predicted when it will come to the stage where we no more have the active Earth. In the Archean, because the mantle potential temperatures were much higher, you had a large generation of basaltic magmas. The oceanic crust was much thicker, maybe around 20 kilometers thick, compared to the modern oceanic crust, which is only 8 kilometers thick, around 8 kilometers thick, and very shallow angular subduction as compared to the Archean subduction system. So there's a fundamental difference. Because of this, the whole convection pattern, mantle convection pattern of the Earth was also different. At present, we have what is called a whole mantle convection. The mantle system is just one huge convecting cell, whereas in the Archean, we had what is called the double-layered convection system. At some stage, there was mantle overturn. Next slide, please. So if you look at the Earth, in total, the plate tectonics is a process, is only a skin top process. It operates on the surface of the Earth to certain depth. Once the oceanic plates go down vertically, they reach the mantle transition zone between 410 and 660 kilometer range. They can no more vertically subduct into the mantle because of the density contrast, and they accumulate there as what's called stagnant slabs. And these stagnant slabs, when they accumulate in large quantities, because of the mineral transformations and density change, they blow down or they avalanche into the deep mantle under the core mantle boundary, where they are recycled by heating from the core, and they rise up at small plumes which coalesce to form what are called super plumes. So you can see that the major part of the mantle is dominated by, or major part of the Earth's mantle dominated by what is called a plume tectonics. And the plate tectonics operates only probably in the upper part. These plumes or super plumes are very important carriers or pipes which transfer volatiles and elements from the core and from the deep mantle onto the crust and into the atmosphere. This is the whole Earth system of plates and plumes. Next slide, please. So we have this introduction to address the remaining part of the talk on so why the life was not born for over, or why the Earth was barren for over 4 billion years of history. And when was the modern life born, where it was born, and why it took so much time for the modern life to be born. So the remaining part of the talk, I'll focus on these small points, these important points. Okay. Next slide, please. So far as we know from the so-called paleontological record, the oldest microbial life forms are reported from some chert formations, what's called in the apex chert in Australia, which are of Mesoarchean age. And these life forms are supposed to be microbial life at 3.5 G, although there is debate over this as well. But this is the oldest reported life form so far as we know. Next slide, please. Next slide, please. We are all very familiar with what is called the banded iron formations and how these rocks trace a major transition in the history of the Earth. One, by introducing the very early life forms of cyanobacteria. Two, by changing the whole atmosphere, because the cyanobacteria can convert and produce oxygen. So this oxygen generating bacteria was flourishing in our late Archean, early Paleoproterozoic oceans at that time. And these oceans were all toxic because early oceans had a lot of metals and elements, and it's a brown colored iron and suspended iron. So this brown colored iron, this ocean was cleaned up by these small organisms by producing oxygen and depositing the banded iron formations, that they themselves dying out as the silica layer in between, then again rising. So the BAFs are one of the important criteria to understand one of the early lives and how suddenly the Earth's the atmosphere changed. Next one, please. Biologists say, there is a biological clock. Biologists say that the blueprint of life means how to make the modern life's blueprint was set about 800 million years ago, although the modern life started only by 500 million years or after that. This blueprint, they say, is what is called bilaterianism. We are all bilaterians. You look at any animal, any bird, both sides are equal, bilaterians. So the bilaterian symmetry was set, or the biological clock was set, although life did not form, because the period from 800 to 500 million years was the most turbulent period in Earth history, with the repeated snowball events, as you know, that repeated glaciation and drastic changes in climatic conditions and the formation of Gondwana, rifting of continents from Rodinia and assembly of Gondwana. So this period, actually, the life initiation was set up, but life started forming only after the birth of Gondwana. Next slide, please. So you know all about the Idiocala of Hana, which launched the sort of modern life on our planet. Next slide, please. People speculate that life formation involved either or both of these matters, what is called chemotrophy and phototrophy. Chemotrophy means life is energy, okay? Life is energy. It's through energy that you create something. You need energy. Some people believe that chemical reactions is what triggered the very early primitive life on the oceans, because the early basalts which erupted were comatites, and when they are altered by seawater, they formed what are the rocks called serpentinization. Serpentinization releases hydrogen ions, and this was the energy which created the early life. Some people think that no, it is phototrophy, the light, sunlight, taking the example of stromatolites, which supported life formation. I mean, which gave the energy for life formation. Next slide, please. A very good example is the pumice class in the apex formation, apex basalt. This pumice has a lot of cavities, class. And you know, pumice floats and accumulates on the coastal areas. And these class contain biominerals, including sulfides, phosphates, and other essential nutrients which can supply essential nutrients for life. So some people believe that early life forms were formed within this class of pumice class. Next slide, please. Essential components for life are the carbon-centered sugar for fuel, and the phosphorus-centered metabolism, and the nitrogen-centered information coding, which is DNA. That means you need supply of these very important elements to support or constitute life. Next slide, please. Next slide, please. So essentially, all these nutrients are coming from rocks. So minerals and rocks are actually the food for life. So the Earth has to wait probably until we had the appropriate minerals and rocks exposed to the surface, their weathering and transportation of the detritus into the shallow oceans, and the nutrient supply before life could actually form and survive. Next slide, please. The best example, next slide, please. Best example is if you look at the world today, continental shelf regions are the paradise for life because there is abundant supply of nutrients. There is visible sunlight there. Whereas you go into the open oceans, okay, they are relatively barren without nutrient supply. And this is the best example of how life is dependent upon geology. Life is dependent upon rocks. Okay. Yes, my last slide here. Next slide, please. My last slide here summarizes the various stages of making the Earth habitable. From the Hadean Earth, which you have seen before, which was completely shrouded in mystery, through the Archean Earth, to the Neoproterozoic with the abundant fluctuations. And finally, the Earth became a habitable planet.
There's no sound. I don't know whether it's from my side.
Okay, I hope you can see me and you can hear me. See me is not important. Hear me, okay. So the first stage is the deep subduction, or what we call as leaking of oceans into the mantle, of the leaking Earth. So once this started, the ocean level started coming down. Ocean water level started coming down. Ocean water level started coming down means the continental new coastline started emerging, lowering of sea level, and emergence of new coastline. That's the next step. When new coastlines emerged, large rivers were born. The birth of large rivers between detritus, deposition of thick sediments occurred. That's what is the next stage. So you have enough supply of nutrients into the coastal zone where life thrived. even then, the land was not habitable because land was still affected by harmful radiation from the sun. So the earth need to wait for excess oxygen to form in the atmosphere, which finally gave birth to the umbrella, the protective umbrella, which we call as the ozone layer. That's the final stage. After the birth of ozone layer, land became habitable. So this is my last slide. Next slide, please. And that's my last slide, that people believe that the life was formed, early modern life was formed in the oceans and later migrated onto the safety of the land when the land became more habitable. Last, thank you very much. That's my talk today, and with Cheng Xie. Okay.
Thank you, Professor Santosh. The questions may be asked in writing and submitted to the organizers there. In due course of time, you will have your answers. Thank you very much.
I must also thank you, Professor Bhargava, for chairing this session, and Professor Banerjee for giving me this opportunity. Not only that, I saw many mails today from my colleagues in India. They were sort of advertising this talk. I'm sure that many of my colleagues are listening to this talk. I must thank all the audience for listening to our talk, and nice to see you all. Okay, miss you all actually. Okay, thank you very much. Thank you, Professor Cheng, for
Wonderful.
Thank
Giving
you.
and Santosh, both are wonderful talks we had. We started our plenary talks with you, and it was really a pleasure to listen to both of you. Our all colleagues all over the world will be enjoying this, especially
Thank
the
you.
Indian colleagues. Thank you.
Thank you very much.
Thank you. Thank
Thank
you.
you, Bhargava, for the
Thank you.
wonderful conducting the session. Thank you.
Thank you.
Thank you. Thank you very much.
Thank you. Okay.
Wonderful.
Bye. Signing off.
Bye-bye.
Bye-bye.
Bye.
Thank you. Thank you very much. Bye-bye. Thank you.
And in this session, we have there was some glitch. I'm sorry about that. So greetings for the day. And this evening or afternoon, we have two eminent speakers. The first in the series is Professor Yan Zelazwicz. And I will introduce the speaker today. Here, Professor Yan Zelazwicz is Emeritus Professor of Paleobiology at University of Leicester, UK. He is a member of Anthropocene Working Group and chairs the subcommission of Quaternary Stratigraphy of International Commission on Stratigraphy. Professor Zelazwicz has authored more than 350 articles and citations, with citations crossing more than 16,000. And today he will be speaking on his one of the very favorite topic. The title of his presentation will be "The Anthropocene as a Potential Unit of Geological Time Scale and Update on Progress." He is joined with his co-author, Professor Francine McCarthy of Brock University, Canada. Professor Yan Zelazwicz, please. Over to you, sir.
Greetings. Francine and I and our co-authors are honoured to be here at the 36th International Geological Congress to outline progress in the study of the Anthropocene. Here is the context showing progress made in the subdivision of the Quaternary period, including the new tripartite subdivision of the Holocene series and epoch. The uppermost stage of the Holocene is the Megalaean, defined in a speleothem in Meghalaya, India. But is there more? In 2000, Paul Crutzen, an atmospheric chemist and Nobel laureate, observed that Holocene conditions had in reality terminated because of enormous recent changes to the Earth's atmosphere, climate, landscape and biosphere following industrialization. He proposed that we are now in a new geological epoch that he called the Anthropocene. Part of the growing evidence for this was a recognition of the Great Acceleration, linked steep mid-20th century rises in both socio-economic trends such as energy use and gross domestic product, and Earth system trends such as atmospheric carbon dioxide levels and nitrogen flux. But is this true geologically? Since 2006, geologists have been examining this question. And since 2009, the Anthropocene Working Group of the Quaternary Subcommission has been examining this question formally. This talk by Francine and me summarises just a small part of the large body of the evidence that has been gathered. The detail has been very extensively documented by the Anthropocene Working Group for those interested in following this up. The resulting majority Anthropocene Working Group view is that Paul Crutzen's hypothesis is correct, and this is our proposal for this part of the timescale. The Anthropocene is geologically real and should be formalised at series epoch level, with a base at the mid-20th century, coincident with the beginning of the Great Acceleration. We can start with lithostratigraphic evidence, with minerals, the building blocks of rocks. The Earth's inventory of naturally occurring minerals is a little over 5,000, an assemblage that has been more or less stable for 2.5 billion years. This graph shows growth in in minerals through all of Earth history. The small step at 2.5 billion years is when atmospheric oxygenation produced a new suite of oxides and hydroxides. There is then an enormous rise from the mid-20th century of synthetic inorganic crystalline compounds. These are minerals in all but formal name, and there are now more than 200,000 of them. Some of them are geologically abundant. These include pure forms of metals and alloys, which are rare or non-existent in nature. An example is aluminium metal, grown from trace amounts to around 500 million tons since the mid-20th century. Enough has now been made to coat all of the USA and part of Canada in standard aluminium kitchen foil. A related substance is plastics, synthetic organic polymers. Since the mid-20th century, some 9 billion tons have been made, enough to wrap the Earth twice over in cling film or plastic wrap. Durable, non-biodegradable and easily transported by wind and water, plastics are now ubiquitous in post-1950 sediments worldwide, as in this beach rock in Spain, and in this deep-sea succession in the Santa Barbara Basin of California. The increase in microplastic concentrations mirrors the growth in global plastics production. The new minerals are components of new forms of strata. The Anthropocene may be brief to date, but it has seen an enormous increase in erosion and sedimentation. Human use of sediment has increased by more than 2,000% since 1950, and human-driven sedimentation is now vastly greater than natural background sedimentation. One form of this sedimentation is that associated with mineral extraction, building and landscaping. This has grown manyfold from the mid-20th century. This anthropogenic sedimentation is most pronounced in urban areas, where it produces geologically mappable deposits of artificial ground. Post-1950 deposits of artificial ground are distinctive lithologically, for instance in containing large amounts of concrete, a synthetic rock produced in prodigious amounts in Anthropocene time, more than 500 billion tons in total, which equals about a kilo for each square metre of earth, land and sea. There are widespread distal sedimentation effects too, for instance in this post-1950s influx of silicate mud onto the deep sea floor off Madagascar, the result of deforestation-caused erosion following thousands of years of slow carbonate sedimentation. There are many Anthropocene chemostratigraphic signals. Here are just a few. There is a large recent perturbation to Earth's carbon cycle, caused mainly by the enormous post-1950s increase in hydrocarbon combustion. Since 1950, humans have expended more energy, mostly by burning fossil fuels, than they did in all of the previous 11,000 years of the Holocene. This has led to the classic Keeling curve of rising carbon dioxide concentrations, systematically measured since the late 1950s. This shows a longer 20,000-year context from the late Pleistocene and Holocene, measured from polar ice. The lower dark blue line shows a slow rise in CO2 across the Pleistocene-Holocene boundary, its general Holocene stability, and then a larger, near vertical rise, most of which is post-1950. The yellow-orange line above shows the corresponding change in carbon isotope values, which plunges over that same short time to a 2 per mil negative carbon isotope anomaly, already being imprinted into organic matter such as wood and shell. The Antarctic ice record allows an even longer context. Over most of this 400,000-year record, atmospheric carbon dioxide has oscillated between normal glacial and interglacial levels, driven by astronomical forcing. In the last century, human impact has overwhelmed astronomical forcing to take Earth's carbon dioxide levels outside of their quaternary limits to levels last seen in the Pliocene epoch. This increase in atmospheric carbon dioxide and other greenhouse gases has led to a substantial heat imbalance on Earth and already sharply raised global temperatures by more than 1 degree centigrade. And however high atmospheric carbon dioxide levels climb, their climate effects will persist for many thousands of years into the future. Industrial hydrocarbon burning produces other geological signals. One is in the unburnt carbon particles of smoke. This is a tiny smoke or fly ash particle, more formally a spherical carbonaceous particle or SCP. SCPs are robust, distinctive and highly fossilizable. Here is a 1,000-year record of peat from northern England. The sharp rise in SCP deposition and that of associated metals is a good marker for the Anthropocene, and Francine will show more examples. The global nitrogen and phosphorus cycles have, since 1950, been even more profoundly impacted than that of carbon. This shows the rise in their use, mostly for fertilizers. Amounts of reactive nitrogen and phosphorus at the Earth's surface are now both more than double their pre-industrial levels. And stratigraphic effects can be seen even in very distal settings, such as these Northern Hemisphere lake records, which show a systematic downturn in nitrogen isotope values from the 1950s. Other signals include those of new synthetic persistent organic chemicals, such as this remote rain-fed Scottish lake, the post-1950s sediments of which are clearly characterized by DDT and other pesticides. There is also an artificial radionuclide signal. Above-ground thermonuclear bomb testing from the early 1950s led to global spread of artificial radionuclides, such as plutonium and excess radiocarbon. Francine will demonstrate some examples later. There is an Anthropocene biostratigraphic signal too. One might start with trace fossils. Here's an example from Cambrian strata. Here is one of our equivalents. Here is another Pleistocene example from Tenerife. It is a fossil wasp's nest built of tiny pumice fragments. And here is a human-made equivalent. This particular human trace fossil system is a part of Shanghai, but such urban trace fossil systems now cover large parts of the land surface. They go deep underground too. Such traces will be very durable geologically. We can also consider body fossils. Biological extinction rates are increasing, we know, but have we already produced a 6th major mass extinction event in Phanerozoic history? The answer is not yet, but with currently steeply rising rates of species extinctions, an end Cretaceous scale mass extinction event is likely within a few centuries. But something that has already happened is a geologically unprecedented suite of biological species invasions between every continent and every ocean on Earth. Successful invaders include the rabbit and the rat, and more recently the zebra mussel from Asia, now spreading rapidly through USA and European waterways. There are many thousands of others. Invasive species now form a substantial part of Earth's biota globally and have reset the course of Earth's biological and therefore future paleontological history. The timing of these species invasions can already be used biostratigraphically, as Francine will show. While the domestication of animals has also transformed biological assemblages, wild animals now make up only some 3% of terrestrial vertebrate biomass. There are yet larger scale changes. For instance, the total mass of the biosphere has about halved since the beginning of human impacts. This has been a long process, mainly by deforestation. While the biosphere has recently been outweighed by the much more rapid growth of functional anthropogenic mass, that is, our buildings, roads, machines, and so on. Within this anthropogenic mass, there are many millions of highly preservable, hyper-rapidly evolving technofossils, which are already imprinting a very high-resolution technostratigraphic record into strata. So this is just part of the evidence base for a chronostratigraphic Anthropocene. So to sum up, the Anthropocene Earth system shows profound and increasing departure from Holocene baseline conditions. Much change is now irreversible. Geologically, the Anthropocene is sharply distinct, as expressed through a wide array of stratigraphic proxies. And the base of a potential Anthropocene series epoch is optimally placed at the mid-20th century. Thank you for your attention. And now I will hand over to Francine, who will describe the kind of detailed correlation illuminated by the ongoing research into potential Anthropocene stratotypes.
Scientists have been analyzing material from 12 sites worldwide to assess their potential as GSSP candidates since May 2019, when a supermajority vote was in favor of erecting the Anthropocene as a formal unit of geologic time, ratifying the informal vote taken in 2016 at the International Geological Congress in Cape Town. The geologic materials being considered to define this new epoch, with a base in the mid-20th century, include coral reefs, a speleothem, a peatland, lake sediments, an ice core, and shallow marine sediments, in addition to anthropogenic sediments from a modern city. Consequently, a wide variety of proxies is being investigated for evidence of large-scale alteration of Earth systems resulting from the rapid increase in human population and technological advancement, the Great Acceleration of Stefan et al. 2015. Analysis of most of the proxies initially envisaged was well underway as of our last meeting at the Haus der Kulturen der Welt, the Museum of World Cultures, in Berlin last September. The Haus der Kulturen der Welt, or HKW, is funding this unique collaboration between scientists, social scientists, and artists whose aims are 1. To identify the best candidate to present to the International Commission on Stratigraphy for consideration of the Anthropocene as a formal interval of geologic time, and 2. To consider the implications of such a designation. Quaternarists are familiar with GSSPs in ice cores, so I'll begin by showing a summary of proxies in the Palmer ice core from the Antarctic Peninsula, where chronological control is provided by annual layer counting validated using volcanic horizons as shown in the image at the bottom left. The methane record, shown at the top right, shows a sharp acceleration in the mid-20th century, with double pre-industrial values of methane measured by 1973. The first fly ash particle ever identified in an Antarctic ice core was observed in the ice layer from 1936. There is also precedent for the use of speleothems in subdividing the Quaternary, so one of the sites being considered is the Grotta di Ernesto, or Ernesto Cave, in Italy. Annual banding, clear in the image at the top right, provides chronological control in the stalagmites. Proxies of anthropogenic impact, such as sulfur, natural fluorescence, stalagmite growth rate, radiocarbon, and stable isotopes, show a response to the Industrial Revolution, followed by a rapid acceleration in the mid-20th century, although some proxies show a lag due to the complex hydrogeologic system. Several of the sections being considered are from lakes, including the annually laminated sediments from Sihailanguan Mar. The varves are comprised of dark-colored diatom-rich layers and light-colored detrital layers. Radionuclides from above-ground nuclear weapons testing is recorded by strong peaks in plutonium-239 and 240, and cesium-137, a little bit higher in the core at 7.7 centimeters, ascribed to AD or Common Era 1963. This places 1950 around 8.8 centimeters, where the dashed line shows up in the two diagrams. And it picks out a very sharp increase in spheroidal carbonaceous particles, or SCPs, and soot, both from fossil fuel combustion. The XRF core scanning also shows obvious fluctuations in the upper 7 centimeters of the core. Annually deposited couplets of dark organic matter, capped each summer by precipitated calcite, provide precise annual resolution across the 23-meter deep basin of Crawford Lake, which is near Toronto, Ontario, Canada. A sharp increase in the early 1950s in SCPs, or spheroidal carbonaceous particles, records rapid industrial expansion following World War II. These particles that you see in the SEM image at the center of the slide result from high temperature combustion of fossil fuels. Changes in microfossil assemblages in the mid-20th century also record major changes in the ecosystem of this small meromictic lake that are associated with the Great Acceleration. The Searsville Reservoir in Northern California, USA, has been accumulating sediments since the dam was built in 1891-92. This has resulted in a highly expanded section. The proposed Anthropocene, for instance, spans nearly 6 meters in this core. Marked seasonal changes in this region of Mediterranean climate allowed very thick couplets to be counted, providing an age model at annual resolution, with seasonal changes, frequent torrential floods for instance, evident in the SCP record. Several other proxies also record a signal of the Great Acceleration, particularly the burning of fossil fuels. This includes stable isotopes of carbon and nitrogen, in addition to SCPs. Also in Northern California, the sediments of San Francisco Bay record substantial anthropogenic impacts since the mid-19th century gold rush. A key aspect of the study in San Francisco Bay is of introduced species, or neobiota, that are the result of unintentional and deliberate processes, unintentional being ballast water from shipping, and deliberate including aquaculture. There is sharp acceleration in the 1870s and then again in the mid-20th century, and these can be incorporated into global chains of paleontological correlation with high precision. Another coastal marine site that is a potential GSSP section is the core from Beppu Bay, Japan. Many proxies have been analyzed in laminated sediments, and there's a clear record of both global and local scale anthropogenic impacts in the mid-20th century. These include SCPs, the fallout of plutonium and other nuclear bomb products, as well as the radiocarbon bomb effect. There's also an increase in total organic carbon, TOC, reflecting an increase in biologic productivity, eutrophication of this site with increased population and land use around the bay. Similarly, in a 45 centimeter long core retrieved from the East Gotland Basin in the central Baltic Sea, a sharp increase in SCPs and bomb products like americium-241 mark the mid-20th century. The age model is based on an event stratigraphy that uses 12 time markers, including the increase in PAHs related to the beginning of the Second Industrial Revolution, DDT appearance in the early 1950s, and the Chernobyl accident in 1986. An abrupt change in the core, various proxies in the core at 27 centimeters, i.e. around 1955 Common Era, corresponds to the beginning of human-induced eutrophication of the Baltic Sea and the extension of hypoxia in its deep basins, which can be seen in the color change in the core. Microplastics were observed throughout the core, even following implementation of rigorous contamination protocols in the end of the 20th century. There's a sharp increase in microplastics during the 1950s, peaking in the 1970s. The legacy of many centuries of mining is recorded in peat from amphitrophic wetlands in Sniecka, Poland, which is near the border with the Czech Republic. Although this is now a popular tourist area, the radiocarbon-based age model records a sharp increase in anthropogenic impact in the mid-20th century, in peat from 2 cores. This reflects the global record of the Great Acceleration, but with a regional overprint from the combustion of coal in power plants and in the steel industry. Corals incorporate young carbon created by above-ground testing of nuclear weapons, what we call the bomb spike, and carbon isotopes record the burning of fossil fuels that are depleted in C13 and contain no C14 at all since the Industrial Revolution. The C13 Zeus effect results from the overprinting of the bomb spike over the gradual decline in heavy isotopes of carbon relative to carbon-12. And on this slide, you see the results from the Flinders Reef in the Great Barrier Reef of Australia. The corals in the flower garden banks of the United States show the same response, with a linear decline in C13 over the past 69 years, but a sharp peak in C14 or radiocarbon during the Cold War. This site in the Gulf of Mexico also records the impact of oil production that is tracked by barium, which is used in drilling mud, in coral skeletons. The proponents of the last site, the city of Vienna, Austria, suggest that its urban stratigraphy, anthropogenic deposits like those from the excavation for the Vienna Museum at Karlsplatz and municipal landfill shown in models at the bottom left, might be useful as an auxiliary section for the Anthropocene. These anthropogenic deposits contain the proxies that are seen in natural archives, including plutonium, although not as finely resolved as at other potential candidate sites and not in continuous sections without facies changes, and the stratigraphy is not readily accessible. In summary, I want to remind you what the requirements are for a GSSP and how the sites being investigated measure up as potential candidates to present to the ICS next fall to consider erecting the Anthropocene as a formal interval of geologic time. The horizon should be dated in a continuous section using markers that can be correlated regionally and globally. All potential GSSP candidates, except for the Karlsplatz archaeological excavation, meet these criteria. But as I mentioned in the previous slide, Karlsplatz could serve as an auxiliary section. The products of above-ground nuclear weapons testing, including the radiocarbon bomb effect, are the favored primary markers to identify the mid-20th century. These have been found in all potential GSSP candidates, independent of facies. Several secondary markers record the rapid technological and industrial expansion following World War II, most notably the combustion of fossil fuels. While secondary markers are useful at different geologic settings depending on the type of geologic environments, all potential GSSP candidates record profound effects on Earth systems in the mid-20th century. The Great Acceleration of Stefan et al., 2015. On behalf of the Anthropocene Working Group, and in particular my fellow team leads, I want to thank you for your attention.
Thank you, Professor Zelazwicz and Francine McCarthy, for making this presentation and a strong case supporting the Anthropocene as a latest division of stratigraphy. And I'm sure that attendees may have some questions on this and queries to be answered. And they are all requested to post their queries in that chat box. And our backend team will mediate with the speakers to get the appropriate answers in time. Thank you so much, the speakers. And the next speaker of the evening is Professor Roland Oberhansley. Professor Roland Oberhansley is an expert mineralogist who has served as a professor of geochemistry at the Johannesburg-Gutenberg University in Mainz, Germany, and later he was a chair of mineralogy at Potsdam University. Professor Roland was president IUGS between 2012 and 16, and also headed the subcommission of magmatic and metamorphic maps of the Commission of Geological Map of the World. He has more than 250 articles and over 6,000 citations. The title of his presentation is High Pressure Record of Cretaceous Salinity Crisis. And he's been joined by his co-author, Franziska Schiefer, doctoral student from University of Germany. Professor Roland Oberhansli, please. Over to you, sir.
Well, I would like to. Is it okay?
Yeah, please. Share the slides, please.
Excuse me, can we see my slides?
Not yet. Yeah, now it's coming up.
Okay.
Here now.
Ladies and gentlemen, I would like to thank the organizers and especially Dirash for the opportunity.
Data on observations that bothered me and my colleagues for decades. This is also a chance to present the results achieved in the doctoral thesis. Today we focus Today we focus on Asia Minor, the Anatolites of Turkey, here the Afyon zone and the Lycian realm. In these metasediments we found strange crystals which had never been described, neither by the stratigraphers nor sedimentologists working in the same area before. The crystals form calcium. In these metasediments, we found strange crystals which had never been described, neither by the stratigraphers nor sedimentologists working in the same area before. The crystals form calcite rods, sometimes up to 2 meters long. The calcite forming the rocks shows suspicious fibrous textures, similar to aragonite fibers, and the overall shape leaves the impression of selenite crystals or gypsum crystals. The calcite rods were not reported earlier. This is astonishing, since over the years, together with Osman Chandan and our students, we found such crystals distributed in the Anatolites from west to east in strata assigned either to Triassic or Cretaceous. Today I would like to focus on southwestern Turkey, especially the Lycian realm and the Uran unit. Gaetan Rimmele defined the high-pressure metamorphic Uran unit based on the calcite rods observed in the marbles and between the cherts. He named these rocks Rosetta marbles. From field observation, it is obvious that the calcite rods occur in different sedimentological settings. We observe them associated with quartz or with quartzite, with marbles, or with chert. Originally, this material was sand, limestone or carbonate, and evaporite, respectively, the rhodiolarine mud. In addition to the facies setting, even depositional features can be observed on these slides. On this slide, I would like to present you the growth orientations of the selenite pseudomorphs. The black arrows in the pictures point towards stratigraphic upwards. Here in A we see dome-shaped fan growing on top of a previous fan. In these pictures we can find subparallel leaning crystals. Here we recognize a fan growing from the overlying chert layer. In these pictures, we can see fans of pseudo-selenite growing from a chert nodule upwards and downwards as well. This case exhibits the growing from a central line upwards and downwards between the chert layers, and the last pictures shows the nucleation from a radiating nucleation from a point. Despite metamorphism, crystal habits and morphotypes of selenite pseudomorphs are still recognized. Rod-like crystal habits in grey marble matrix, and the rods consist of fibrous calcite. Note the pushed forward tip of material, brown material at the top of the crystal. We also find swallowtail crystals, fishbone-like crystals in a quartzitic matrix, Christmas tree-shaped selenite pseudomorphs of almost dendritic habitus, skeletal textures, bunches of saber-like crystals, and in the last picture we see the front of the crystals in the layer. Images on the top view of the calcite rods render recognition as pseudoselenite more complicated, but in some cases it is still possible to recognize the selenite crystal shape clearly. Random cuts, however, leave the impression of a calcite breccia, and only careful, detailed observations can allow for the recognition of pseudo-selenite phenomena, like here a twinning plane. Large-scale horizontal in-plane metaselenite textures at bedding planes are striking and add to the enigma why these features were not described earlier. On top we see radial appearance of selenite pseudomorph fans in carbonate with free growth, and the bottom shows more complex textures when there is more concentrations of the evaporites, probably higher concentrations in the brine. The brine. This view of a chert Rosetta marble layering exhibits a striking phenomenon. Imprinted in the cherts, we find shapes that look like selenite crystals. This indicates a syn-sedimentary deposition and the formation of the gypsum or selenite crystals at depths and not in the evaporitic laguna. The macroscopic field observations led to the definition of different stratigraphic and sedimentological settings, implying various depositional depths for different sites. The first section shows a proximal association of evaporitic material with sandy material, here pseudoselenite on quartzite. The second section combines thick evaporitic or marble layers with continuous chert layers. And this is the typical Neothethian hemipelagic sequence. In this marble layers, the selenite crystals can grow very big, and there is a considerable amount of selenite crystals. The third section is a thinly layered section, intercalation of chert, Rosetta marble, wacky stone. And in these sediments, although the evaporitic minerals can still be found in the Rosetta marbles, they are less frequent. Remarkable, however, in both sections, we found relicts or pseudomorphs of radiolaria. In the cherts on the one hand, but also in the wacky stone, these rounded recrystallized quartz objects are thought to represent the radiolaria. I would like to give you a more convincing impression by comparing the findings in the Rosetta marble, here on the right side, with examples from neogene selenite deposits. The similarities or distinctiveness of the Rosetta marble shapes is striking and reassuring with respect to the field-based interpretation. On the top, we compare the swallowtail twinning. In the central part, there is a comparison of horizontally radiating selenite in the bedding plane, and at the base we can see radiating selenite or gypsum crystals perpendicular to the bedding in the neogene and here in the Rosetta marbles. The same is obvious for details on the base of a single crystal. Again, on the right-hand side, our Rosetta marble shapes and the fresh gypsum or selenite crystals in the neogene example. On top, we find large Saber crystals. They can still be found in the Rosetta marble. Obviously, there is these curved Saber crystals in the neogene gypsum deposits. Very similar, we find these Saber-like crystal shapes in the Rosetta marbles, here again nicely with the fibrous structure of the aragonite. In the neogene, one also can find gypsum crystals with a twinning plane. In the twinning plane, there is always a little bit of muddy or carbonaceous material. The same holds true if we can find single crystals or twinned crystals in the Rosetta marbles. All this is remarkable since the Rosetta marbles occur in areas that experienced blue schist metamorphism. Let us look now to the tin sections. In tin sections we find some monoclinic outlines of crystals, not very typical for calcite. We find fibrous calcite, which we interpreted as aragonite pseudomorphs, and there are areas in these two circles where we have a strong recrystallization of the calcites, very late recrystallization of calcite. If we look at the same spots under the cathodoluminescence, this images a striking feature showing that the primary trace element zoning is still preserved, respectless of the later recrystallization, either as fibrous calcite or as very fresh, minute calcite crystals. So, primary trace element zoning is preserved despite the recrystallization. The previous slides showed the similarities of the calcite crystals to selenite. The interpretation of the calcite as pseudomorphs of aragonite bases on the fibrous aspect of the calcite in the field and on the high strontium content up to 3500 ppm. Even the non-fibrous calcite exhibits elevated strontium content around 2000 ppm, as shown in this microprobe element mapping. Strontium is not compatible with the trigonal structure of calcite. In the six-fold coordinated unit cell, only calcium and the smaller ion magnesium would fit. The polymorph aragonite, however, is orthorhombic, so it's a dressed-up structure. The unit cell is nine-fold coordinated, thus bigger, and here strontium can fit. So that's one of the reasons why aragonite can be detected at the base, or pseudoaragonite can be detected at the base of the strontium content. Strontium was originally included in the evaporates, of course. Minute quartz inclusions in the Rosetta marbles contained very small crystals that we could identify as aragonite by Raman spectroscopy. And this testifies to the high pressure metamorphism on all of these rocks. Now, for the area, the blue schist metamorphism has been recognized by several authors and compiled in a schematic PT diagram. I present a general subduction geotherm here in blue. The gypsum anhydrite transition in green. At low pressures, it's a direct transition. At higher pressure, basanite would form. In black, there is the transition of calcite to aragonite, and the black symbols here is the data from the urine unit metaphyletic layers reported by Rimle. It's the blue schist overprint of the whole area. In addition to that, I show you in yellow the PT path ending in the blue schist field reported by Amaury-Pourtot for the whole of the Afyon zone. And we took very minute fengite inclusions from the muddy matrix in the Rosetta marbles, analyzed them, and using the method of Dubac, were able to show that these also point to growth under blue schist conditions. So in a nutshell, the Rosetta marbles experienced blue schist metamorphism. Let us take some conclusions from the observations. Now, the radiolaria point to pelagic, hemipelagic environment. The selenite imprints in chert indicate that the gypsum crystals formed at depths. Aragonite indicates that the rocks underwent high pressure metamorphism. The calcite fibers point to a phase transition from aragonite, and that there is no ion transport since strontium is still there. The cathodoluminescence tells us that primary features are preserved and implies no deformation and no material transport. To unravel the PT path of the Rosetta marbles, the preservation of selenite shapes is major, since a transformation from gypsum to anhydrite would result in the loss of shape. Therefore, a pressure increase at low temperature is needed. Selenite crossed the calcite aragonite transition before crossing the gypsum anhydrite transition. According to Machel, thermochemical sulfate reduction along a subduction geotherm takes place at low to moderate elevated temperatures between 100 and 180 centigrades, but within the pressure field of aragonite. So this gives us this red space where a transition with the thermochemical sulfide reduction reaction, methane, calcium sulfide leading to calcium carbonate, H2S and water is possible. This interpretation is of course in line with the observation that the selenite pseudomorphs show high concentrations of strontium, and this is true for the whole of our findings in Anatolia. I now would like to show you an isotope plot with oxygen versus carbonate isotopes. The sample sites are shade colored and the stratigraphic level within the sections is equally color coded. Almost all samples plot in the 68% confidence field of mean Cretaceous seawater after Geyser. Most of the samples plot within the field defined by Geyser, and only some parts from the Thessalian and especially the Karabe-Ürtelen, the deep section, show clusters according to the stratigraphic position within the section, differing from the main setting of isotopes. So the general observation is primary carbon and oxygen isotope signals of the mean Cretaceous seawater are still preserved. If we look at the carbon isotopes, we can see that the carbon isotopes are more dependent on their stratigraphic setting. So they correspond to different phases. While some sections are really homogeneous in their composition, like Achakaya, the middle one, and also more or less the section in Thessalian, although at the base it starts with more quartzitic material while there is more carbonaceous material at the top. The longer section in Karabe-Ürtelen then shows this very strange deviation. We can conclude that there is a locality dependent composition of the carbon isotopes, and this is lithology dependent, so this is a chemostratigraphic phenomenon. Let us now consider some Rosetta marble rods, and here you can see that even at the centimeter scale, the different objects in our Rosetta marbles, the rods, the intermediate matrix, some other parts of the matrix and the fringes show a completely different composition. This is more clearly visible in this presentation, where you can see that metaselenite matrix mix and rod fringe material cluster in the oxygen isotope, carbon isotope diagram and represent the fact that isotopes did not change over the recrystallizations. Our interpretation then is as follows. During arid periods, there was areas which we never identified where the hypersaline brine was produced. Spillover allowed the brine to migrate downslope we have the formation of selenites in intermediate basins and under the conditions of very normal marine seawater. The further distal we go, the more carbonate can precipitate. During humid times, two major changes occur. One is that the riverine or continental input increases, calcic turbidates go down the slope, they intermingle with the selenites in some of the basins. Further down, we have the normal seawater, cold seawater that is upwelling and bringing nutrition, so the deposition of radiolarian mud on top of the selenite is possible, and this setting corresponds pretty nicely to our observation of the three sections described in the Lycian realm. Let's keep in mind that the phenomenon Rosetta marble is of rock-forming character, and it is very distributed. Just for the Afyon zone here in the light blue, the thickness of the marbles ranges from 1,000 to 500 to 2,000 meters, and the lateral extension today is more than 600 kilometers. So this is a regional and not a local phenomenon. I hope I could convince you that the data presented from the blue schist metamorphic Rosetta marbles stands for an impressive mid to late Cretaceous salinitic crisis. And the record calls for massive brine spillover leading to the observed intercalation of evaporite pseudomorphs with chert. The information beyond evaporitic realms, as well as the subduction type metamorphism, has to be considered in paleogeographic reconstructions, as this is partly expressed in this reconstruction from the Darius program working on the Middle East basins. Thanks to all my students and colleagues, and thank you for your attention.
Thank you, Professor Roland Oberhansley. It was really a very fascinating talk, and you showed some very interesting sedimentary and metasedimentary features. And I'm sure this audience may have some questions on this. And as earlier, I request all the audience to please type their questions, send us to us in the chat box, and they'll be answered soon. And with this, I thank all the speakers of the session, Professor Yan Zelazwicz, his co-author Francine McCarthy, and Professor Roland Oberhansley. Thank you very much, and I thank the IGC organizing committee, and especially Professor D.M. Banerjee for giving me this honor to moderate the session. Thank you very much, and I now close the session.
Thank you, Rolly. Thank you, John. Thank you, Francine, everybody, and Francisca for wonderful lectures. We enjoyed it, and I think the audience all over the world must have enjoyed it. Thank you again. Okay, we'll see you tomorrow.
Thank you, Dheeraj. And Jan, you finally convinced me. I was still very susceptible about the Anthropocene as a geological formation back in Cape Town.
Okay, well, I'm glad. Thank you, Roland. And I enjoyed your talk too. It's nice to get such a story out of such high pressure, high temperature rocks. So